Hi everybody. So in this lecture, we are going to see how we handle permanent failures in designing of a key value store. So till now we have looked into how to handle temporary failure through hinted handoff. Now we will look into how we handle permanent failure. So what is a permanent failure? So permanent failure happens when, as the name suggests, a server node is permanently unavailable. So how do we handle this case? So here we follow a protocol which is called anti-entropy protocol. And what does the name suggest is we compare each data pieces on the replicas and update each replica to latest version. So let's understand this with an example. Say suppose I have this server 1 and server 2. Server 1 holds data from key 1, key 2, let's say key 8, key 9, key 10. And S2 now holds a key 1, key 2 up till key 8, and it is down before key 9 and key 10 has been written into S2. So what our anti-entropy protocol says that S1 and S2 compare each piece of data, detects that key 9, key 10 are missing, and to minimize the amount of data movement, what we want to achieve, we perform is like once the data has been detected, like which data are missing in server 2, we detect those data and move only these data to a new server which will further hold the replicated data and which will act as a replicated server node for S1 if we consider S1 to be the coordinator. So now S3 will hold key 9 and key 10. By this, what we achieved is minimized data movement, and also we reduced network overhead. So this is our goal. So anti-entropy protocol, as it mentions, that we compare each piece of data and then move the missing data to a newer server or a newer replicated server, which will now further handle the data replication part. To perform this step very much efficiently, we now introduce a architecture, or you can say a data structure, which is called Merkel tree or a hash tree. So what does Merkel tree or hash tree define? So we now understand with an example what is Merkel tree or hash tree. Basically, Merkel tree or hash tree is you can see a kind of trees data structure where every non-leaf node is labeled with hash values of the labels, or values in case of child, or in case of leaf node, values in case of leaf node of its child. So this is the definition. We'll understand it very soon with an example and it will be much more clear. So it says like it is a tree data structure, and the non-leaf node, what it holds is the hash values of its child nodes. So let's say we have 12 keys. Okay. So now we have 12 keys, and we'll look into how this Merkel tree helps us in detecting the data inconsistencies. So suppose this is server 1. So step 1 is example 12 keys. These keys are numbered K1, K2 till K12. Okay. So step 1 is divide these keys into buckets. Let's say for each server. So let's say we form 4 buckets, 3 keys each. So for server 1, I have 4 buckets like this, and for server 2, I have 4 buckets. And let's say server 2 is the server which goes down after a certain point of time. So the data stored in server 1 is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 11, 12 has not been written here, and S2 is down. So now next step, what we do is we calculate hash values of each key. So let's say 1 goes to 101, 2 goes to 102, and like this 12 goes to 112, and this is for every key in each server. For every key in each server. Now, by going by the definition of Merkel tree, which says that every non-leaf node is labeled with hashed values of the labels or values in case of leaf node of its child. So, these are leaf nodes whose hash values have been calculated. So, for every non-leaf node, we need to label it with the hash values of the leaf node or the root node or the child node, sorry. So now we calculate the hash values for a particular server. Okay, so this is, let's say I'll draw a little bit lower so that I can draw the tree above it. So let's say this is server 1, so 101, 102, 103, 104, 5, 6, 7, 8, 9, 110, 111, 112. This is the server 1. These are the hash values of the keys, and this is for server 2. I have 101, 102, 103, 104, 5, 6, 7, 8, 9, and 110. So I calculate the hash values of each bucket. So let's say this is 1001, 1002, 1003, 1004. Similarly for this is 1001, 1002, 1003, and this is, let's say, 999. So now by definition I will use these child nodes to calculate the parent node and thereby go to the root. So comparing, where did I go? Come back, yes. Okay, so comparing these two, I get 1003. Let's say 1003 is already there, so I'll do 2003. These are some random values I'm picking. This could be anything, and comparing these two, this is 2004. And comparing these two, I get 3001. Similarly, comparing these two, since these are same, we will get 2003. Here we get 2006, let's say, and comparing these two, I get 3008. Now, how do I detect that which data or which key in which bucket is missing, or there is a data inconsistency between which keys in server 1 and server 2. So we traverse the tree from root to the leaf node. So we compare the root node first. If both is same, then there is no data inconsistency in both the servers. But if here we see 3001 and 3008, so not same. Now we compare, we recursively do it for the left tree and the right tree. So we compare the left node of this root node, and since both are same, that means everything below it are same in both the servers. So now we compare the right nodes 2004 and 2006. So this is not the same, so we go in the right part of this tree. Now we compare to the left node of this node. So we see 1003 and 1003 both are same. So we do not go down this node. We look into the right node again. We go here, see they are different. So it says that the keys in this bucket and this bucket have some inconsistency. So now we can compare for these buckets the keys, the hash values, and if any hash value is not present, then we can say that in this case 111, so it means 11 is not present, and in this case 112, so 12 is not present. So key 11 and key 12 is being missing on server 2. And by this, with minimal movements, with logarithmic in this case, since it's a binary tree, we can say that we have reduced the data comparisons between both the servers in case of finding the inconsistency. So you can say, using Merkel tree, amount of data to be synchronized is proportional to difference between two replicas, and not the amount total, and not the total amount of data. See, as we can see from this above example only, we are not comparing each data one by one. We are comparing the hash values, we are comparing the non-leaf nodes, we are comparing their parents. If we see they match, we let them go. We do not compare these values. Whereas if they do not match, it means there is some inconsistency in this part. So we keep on doing the same similar in a recursive manner. We check, they compare their hash values for both the servers. If they match, then that means the below keys also match in both the servers. If they do not match, we go down and check for left and right node, and we do this recursively. So we do not compare all the keys in this scenario with the help of Merkel tree. So Merkel tree, what it does is it reduces the amount of data to be synchronized, and this is proportional to the difference between the two replicas. So here difference was 2. So it is proportional to 2, some k times our k of 2, you can say constant 2, and not the total amount of data. So this is the benefit of using Merkel tree. So Merkel tree helps in detecting the inconsistency between the two node pairs, inconsistency between any two nodes, and thereby detecting the inconsistency we can minimize the data movement and thereby reduce the network overhead. Another thing, apart from this, any server going down, having it a permanent failure or a temporary failure, there can be another failure which is a data center failure. Whenever a data center failure happens, all the server nodes in that data center, let's say server 1, server 2, server 3 are here, goes down. So for this, data center is down means all the server is unavailable. So for this, what we do is we try to replicate the data across servers which are in different data centers. And by this, we can achieve the system unavailability. We can achieve the system we can reduce the system unavailability condition, since if a particular data center is run and one server is not available and the data has been replicated to another server which is in different part of the world or with different part in different data center, then we can fetch the data from that server. So by all these methods, we can handle and detect failure and handle the failure, be it permanent node failure, temporary node failure, or be it a data center failure.